Euclidean distance. Euclidean distance is measured using Pythagorean's theorem, whereby if we have 2 points in space, like we see here and here, we can measure the distance between them by the length of the hypotenuse that you see here on this right angle triangle. The hypotenuse is equal to the square root of a squared plus b squared. And that's what we see over here. C, the hypotenuse, is equal to a squared plus b squared. And in this particular case, that ends up to be 3.16 distance units. Within a raster, this is made slightly easier using the link node model for distance calculations. In a link node model, we have one lateral link, which is equal to the resolution of a particular raster layer, and then a diagonal link, which is the square root of 2 units, or 2 times the lateral size or resolution. And these are the only possible directions that things can go in a raster, are laterally and diagonally. And so it makes the calculation of distance very easy within a raster layer. So for example, what if we wanted to know how far this point is here from Simard Hall at the University of Ottawa? We can create a distance surface or distance raster. A distance raster represents for each cell the closest straight line distance back to the source. In this case, the source of this distance layer that you see here is Simard Hall. And so every cell represents how far it is from Simard Hall. So no matter where we are within this geographic domain or extent that we're looking at here, any cell tells us how far it is back to Simard Hall, the source from which the distance was calculated for every cell in the raster. In this case, this point right here is 1,372 meters from Simard Hall. In a Euclidean distance raster, every cell then contains the distance to the nearest feature source, where the feature source may be one cell or multiple cells. You can also have multiple feature sources. And no matter how many feature sources you have for a Euclidean distance surface, each cell will always measure the shortest distance to the closest feature. For example, here we have multiple sources. We have Simard Hall and Father and Sons, a small pub near the University of Ottawa. And we compute a distance surface based on these two features. And any particular area, such as where the yellow dot is, happens to be 284 meters from the closest source. We know which source that is by looking at it. We know that's 284 meters from Simard Hall and not 284 meters from Father and Sons, simply because we can see the sources. But without the sources themselves, the distance just tells us how close it is to the nearest source feature. And we'd have to guess which one. To know with certainty to which source cell a distance value belongs, we need to look at this surface together with what's called the Euclidean allocation surface. A Euclidean allocation surface is something that is created or can be created at the same time as the Euclidean distance surface. In this case here, we have 3 source features. Feature 1, which is in this cell, or was in that location, I should say, not in the cell, but in the location of that cell. Feature 3 and feature 2. Every cell, for example, for feature 1 right here, that is purple, is a cell which is closest to feature 1. Every cell that is green is closest to feature 2. And every cell which is red or pink is closest to feature 3, right here. And so a Euclidean allocation surface divides the space up into zones of influence, for example, or source zones, so that within each Euclidean distance value, we can find on the Euclidean allocation surface for the same cell location to which source that distance belonged. These are similar to what we call Thesen polygons in vector space. So here, for example, is a Euclidean distance surface. That's a Thesen tessellation of that Euclidean, this is a Thesen tessellation of space around each point. And if we overlay that with the distance values for the distance raster, we can see a relationship in the way distances look on the distant surface, where we see these fine lines that divide the space between features. So for example, this line right here, everything to the right of that line is closest to that feature. Everything to the left of that line is closest to that feature over here. And so it tells us which parts of space are closest to which feature. And that's called a Thesen tessellation. And it's very much like the Euclidean allocation surface, but far more exact because it's computed in vector space. We can create a Euclidean allocation surface using the Euc allocation function of Spatial Analyst, where all we have to do is specify the input vector representation or raster representation of the vector features, either one is fine, and then the field that provides a unique identifier to each of the source features. So for example, buildings might have building name as a unique identifier that we want to carry over so that we know the name of each building belonging to each allocation zone. In vector space, we can use the create Thesen polygons in the analysis toolbox. It takes the name of an input feature set, like these points, the name of an output, and then which attributes to carry over, such as all. And so all the input point attributes will be associated with the attribute table of the Thesen polygon tessellation, so that you know which point belongs to every single polygon. That's often used as a means by which to have a first look at increasing the dimension of a point set to a continuous tessellation or complete space filling set of polygons. We can also have a Euclidean direction raster. In a Euclidean direction raster, each cell receives the cardinal direction back to the source cells. And you can even see here, for example, where we have the division induced by locations or cells which are closer to this feature than all other features. So you can almost see the Thesen tessellation in this type of a classified raster. Now, these cells will give direction back along the entire range of the compass from 0 to 360 degrees. Here they're just symbolized into zones. So 0, for example, north, 0 to 22.5, northeast, 22.5 to 67.5, etc. But any cell you happen to select, let's say this one here in the blue area, well, it will have a value that might be, for example, here, west, and that could be about 245, like so. And every cell will have such a value in degrees back to the source. And that can be useful in a number of circumstances. But it's a specialized product of the Euclidean Distance toolset in ArcGIS Pro. Let's look at a Euclidean distance example, allocating geographic space to Winterlude venues. On the right, you can see a number of different Winterlude venues in blue. The city needs to know, for each venue, what the approximate population each venue is required to serve. They need to know that for things like sanitation, how many porta potties to bring there, what type of food services should be allowed, or in how many, and things like that. And so we can use the Euclidean distance as a means to allocate space to each of these Winterlude events. The Euclidean allocation tool outputs distance, allocation, and direction rasters. So for example, if we have a spatial domain and extent set up in our environments, we can have buildings, locations of these particular venues. Send that to the Euclidean allocation tool and have 3 different rasters output. One with the Euclidean distance, one with direction, and one with allocation, or just one of those. So there's no requirement we need all of them, but we can have all of them with that single tool. Likewise, in Python, we can do the same thing, except in Python, we specify Euclidean distance, allocation, and Thesen polygons are another possibility in vector space. And generally, if we're working with vector data, we would use the vector approach completely. And the direction is another separate tool as well in Python. So we go from individual points to polygons, where each polygon represents a space, where each location within that space is closer to the source polygon than any other polygon within that spatial domain. We also have a distance surface and a direction surface, although we don't need the direction surface and probably the distance surface for this particular example. Another example is you may have a list of properties and you want to determine the distances from each of the properties to the closest amenity. For example, the closest school, healthcare facility, recreational facility, mass transport stop, etc. And use these distance-based measures and surfaces as a tool in the production of an index for the quality of life within an urban region. You can think of other ways in which Euclidean distance might be used, as in Raster. For example, the proximity to coast, proximity to roads and salt content, proximity to roads and the occurrence of some species, or mortality of some species, incidence of disease and proximity to source contaminants. These are all possible things for which Euclidean distance surfaces can be used as a measure or model of particular outcomes.